Thank you so much for coming. This is all about building CS50 with GitHub. My name is David Malan, and I teach a course called CS50, or Computer Science 50, Introduction to Computer Science 1 at Harvard. And I thought I'd give you a sense of some of the problems we've struggled with over the years, some of the solutions we've implemented, for better or for worse, and ultimately tell a story about how many now off-the-shelf tools we have integrated into building what is ultimately this introductory course. So we begin each semester with a little bit of a look like this, with a lot of students in attendance who very quickly realize the wonders of videos online. And so ultimately we have about 800 students in the class on campus. But we also have these other demographics as well. And all of them are here ultimately for this introduction to computer science. And I dare say we're a little traditional in that. We focus certainly on abstraction and on data structures and on algorithms, transitioning to look at memory management by way of C, which is the language in which we teach much of the semester, transitioning toward the end of the semester to web programming paradigms and database schemas and the more modern UIs with which students are familiar. But ultimately, students fall into at least 3 of these categories. We have some 800 students on campus, as well as, curiously, a couple of hundred students at Yale University as well, where the course is now offered. But we also have this initiative called CS50X, which is an online MOOC, or massive open online course, whereby the course is freely available as open courseware via edX.org. And at last count, we had some 1 million registrants, not all of whom certainly engage over time, but who are engaging on a weekly basis on the order of tens of thousands of students and thus users of all of our platforms. And then lastly, do we have a third demographic, CS50AP, for advanced placement, which is an adaptation for this course for high school audiences that actually satisfies one of the College Board's new computer science programs. Here, then, is the picture of the demographics that we have. And this paints a picture, perhaps, of the scale on which we've aspired to operate. So not only are students in this course doing their work, they're submitting their work, we're reviewing their work to different levels of engagement based on the type of student that we have. And so how do we actually go about doing this? Well, we've struggled with a few problems in the past, and thankfully tools like GitHub have been helping us solve these for some time. The course itself has a lot of web-based applications via which we allow students to interact with material and follow along. And so, of course, using something like GitHub and Git more generally to actually develop these apps, not just myself, but our team of teaching assistants, many of them undergraduates and students themselves, has certainly been a common workflow. Deploying apps these days using services like Travis so that we actually deploy those apps that we do develop on our local machines, pushing them to services like GitHub that then triggers, as most of you may know, a post-receive hook of sorts that then ensures that your code is actually in some cloud provider, and we happen these days to use AWS. And then even things like hosting documents. For the first 7 or so years out of the 11 years I've taught this course, I was using, say, Microsoft Word, and there was one person in the world who had access to the source of these documents. So whether or not there was a typographical error or an opportunity to make something better, you had to have physical access to my hard drive, which certainly is not the ideal approach when we have such a large community of folks who could find these mistakes and even help contribute solutions. And so nowadays, do we use GitHub Pages and Markdown or AsciiDoc to actually generate the course's documents as well? But there remain some problems in the present, and we've spent several years in implementing different approaches to these, a few of which I'll share here today, and to ultimately emphasize just how consistently we, I think, made mistakes and implementing more than we needed to and home-growing more solutions to problems than we needed to. And these, I dare say, are the 3 problems on which we focused over the past year. Students doing work, students submitting their work, and teaching fellows or teaching assistants actually reviewing this work. So this past summer, a few of us set out, myself, Kareem, and Chad, 2 of whom are here in the front row if you'd like to chat with us later today, Brian and Haley back home, to address each of these problems we hoped in a better way. But this was only after having, again, made a few mistakes along the way. Students doing work, we have generally solved with a homegrown tool. Students submitting their work to the class for review, we've generally solved with a homegrown tool. Teaching fellows reviewing work, we've generally solved with a homegrown tool. And I dare say this is not uncommon within higher ed, certainly among CS faculty, probably myself included, who all think we can do it better than everyone else. And that's why we tend to work perhaps in these silos and certainly not necessarily sharing as many solutions as we might. But allow me to propose the approach we ultimately took ourselves over the years. We did start some 11 years ago with a homegrown tool, and then after writing some enhancements to this, did we have an improved homegrown tool, followed by a new homegrown tool, a new and improved homegrown tool, and then thank God did we get to sort of present day when we stopped reinventing these wheels and started using more off-the-shelf tools that were available, as well as were becoming in vogue in industry, certainly, and becoming standard practice, so that we could actually build albeit with the one little homegrown tool was our first instinct. But no, even that we decided to put aside and use something like Docker. And I'll share with you why we actually had to bring to bear some of these actual ingredients. So for the context here, it wasn't just that every year we decided we could do better than the past. Like, it was an evolving platform, it was an evolving course and curriculum, and evolving technologies for the students. So back in the day, in the late 90s, when I myself took the class, and then in the mid-2000s when I took over the class, students would SSH, or way back in the day, Telnet, to a server that might look like this. They all had a home directory on the server, or the cluster of servers using NFS shares or a network file system to actually share their home directories on multiple computers. This was a wonderful topology because then everything was centrally managed. Everyone was on effectively the same system, but this was managed by Harvard's IT folks. And there was tens of thousands of other users using these systems. We didn't have the requisite root access with which to upgrade software, configure things ourselves. We didn't have very easy access to students' own submissions because we ourselves were just authorized as users on the system. So a few years later, came out nice.harvard.edu for the new instructional computing environment, which, fun fact, 23 years later is still operating at these URLs if you SSH to them, or these host names if you SSH to them. And it was little different other than a, I think this is a function of static electricity, because literally every time I touch the computer, I shock myself, and I thought I could power through. There we go. All right. So I'm going to try to move a little less here. So that was phase 2 for us. And then cloud services came into being. So sort of in the late 2000s, when services like Amazon were coming into play, we actually realized this was a technological opportunity for us to actually migrate the same kind of topology that had worked pretty well for us on campus with this shared cluster with all students on the same system, but one that we could actually control ourselves. And so we actually had a load balanced cluster of workstations running some variant of Linux. We used NFS to load balance, as this picture suggests here, so that all students instead started SSHing to cloud.cs50.net instead of to Harvard's own cluster, which was a great pedagogical improvement for the class. The price, of course, we paid there was that now we, the instructors, had become our own system administrators. So there was that price we paid. A few years later, did we transition to something a little more distributed. Long story short, the course has long supported OpenCourseWare, where everything is made freely available to anyone who wants to tune in online. But for many years, it was a very passive experience. You could download the distribution code, the problem sets, but you couldn't really engage with the course or do the problem sets because you didn't know what environment variables we had set. You didn't know what versions of the compiler or debugger we were using. So a lot of the burden was on students online to actually install everything themselves. So we instead shipped a Fedora-based initially, and then an Ubuntu-based virtual machine, otherwise known as an appliance, that students could download along with a hypervisor or virtual machine monitor and run a Harvard-like environment on their own computers, even if they weren't themselves Harvard students. And then most recently, and lastly, have we settled on CS50 IDE, which is actually a pedagogical layer, a set of plugins on top of a service called Cloud9, once a startup, now one of Amazon's web services, so that students have all of the same features, and as this screenshot suggests, file management, tabbed code windows, all the features you might expect in a lightweight IDE, but as well as, and most importantly, a terminal window in which they have a full root access over a container, a Docker container, underneath the hood. So what are the processes by which students have historically submitted? Back in the day, and even when I took the course, there was a setuid script running on that central server, which meant that whenever you ran the command, it didn't run as you, it ran as root, which meant that the script could see your code, could put it in the course's account, and actually do whatever work it needs to get it to the teaching assistants for evaluation. The interface was pretty arcane, so we improved upon that with something called CS50 Submit thereafter, essentially wrapping some of the university's own code to make it a little more user-friendly. But then we transitioned to something called GitHub FI. That's a firewall installation, which some of you might have used. It predates the current API, and it was a little bit of work on our end to actually get this up and running, and the API wasn't as rich as it once was. But we experimented with this with one of my other classes at Harvard's Extension School, or Continuing Ed program, where we actually decided, well, let's try to hop on this wave of interest in distributed version control and actually give students exposure to Git, and something that they would then benefit from longer term. And so we had them each have their own repositories for their projects, and we had them run a git add, git commit, git push, and so forth to actually get their code onto the servers. And unfortunately, it was a disaster, not because of FI, but really because of the demographic we had at the time, and because of the stupid little things that were sort of besides the point. Git, as you may know, tends not to like it if you accidentally have another .git directory as a subdirectory, because then it gets sort of blacklisted from actually pushing it to the server. And that's fine. It's fixable, but it's not very conveniently fixable. And the burden then falls on the TAs to help students with this. Students didn't realize, and the students' demographic didn't necessarily know what .files or hidden folders are. And so they would think nothing of just making a copy of their folder, moving their code around, and then they go to try to submit a second time. But because there's now no local .git directory, because they didn't even know it was there, and they're trying to push on top of commits that are already on the server, you would get conflicts. And so those two were sort of difficult to resolve. So all solvable, but completely beside the point, when in this class we were trying to focus on implementing solutions to software problems and teaching students to program better, and not getting hung up on things that really were rather intellectually less interesting. And so we transitioned from there to another tool, CS50 Submit. This one web-based that used API keys that students would generate server-side, and then they would just run a command at the command line to push a zip file of their code to an HTTP-based API to the server, where it was then stored for their TAs. And we improved upon that a year or so later with an actual GUI, just for those students even less comfortable, so to speak, with computing and perhaps that command line. And then we're back at present day, where we have this command, submit 50, which if anything suggests that we never really agreed internally on what to call these things over the years, because the names of these tools have changed as much as the underlying technologies. But really what's now underneath the hood is GitHub, or most recently GitHub plus Docker, which solves two problems for us, not just the submitting of work, but also the reviewing of work. And what do I mean by this? Well, here too, I have to stop moving my feet. What's that? I could. You don't think? All right. So we'll do a little Mr. Rogers here. All right. So maybe I should just be behind the podium. OK. So this was not part of the plan. All right. So we'll see if the socks have to go next. So in terms of reviewing work, back in the day, too, this has been an evolution. I should not tempt fate. So we should. We used to use paper. Back in the late 90s, students would print out their code and the TFs would physically mark on it. We eventually learned about PDFs, and then we would annotate things with Acrobat or Bluebeam or some tool like that. And then we came into the mix, that same tool as before, CS50 Submit, which actually had this type of user interface. Long story short, at this phase in our development, we were especially eager for the TFs to be able to provide certainly more convenient reviews of students' code, but also start to collect the quantitative data that had long been lost thanks to paper and PDFs, knowing what kind of comments the teaching fellows were writing and how frequently they were providing feedback, at what length they were providing feedback to students, which students were actually reading their feedback. So there's a lot of pedagogically opportune data that we had never had access to that we finally did once we had an environment like this. And as you can infer perhaps from the sticky notes, it was very similar in spirit to what you might see in any kind of annotation tool today, even though this was several years ago. But of course, you might be familiar with GitHub.com hosting something very similar in terms of code reviews. And so ultimately, did we find that by using GitHub underneath the hood, wrapping it with only those features that we strictly needed, have we been able to put together a pretty robust solution for all of these demographics. So why? What is it that we actually need to solve these several problems of students doing work, submitting work, and the teaching fellows reviewing that work? So we need a client via which students can submit their code, whether it's command line or web-based. We need a server actually listening so as to receive that work and store it somewhere on disk. We need a UI for code review, much like the one we ourselves have implemented. And really, and this is the anomaly for us, we needed a permissions model that was a little bit flexible. We have teaching fellows in Cambridge, teaching fellows in New Haven. We have instructors in both cities. We have students in both cities. And we literally have tens of thousands of students following along via OpenCourseware online, all of whom should have federated access to different types of data and different subsets of the data. But wonderfully, too, in something like GitHub, you have the notion of teams and contributors and user permissions. So that, plus support for things like post-receive or post-commit hooks, really gave us, so that we could trigger auto-grading, really, this was the menu of things that we got out of using a third-party tool like GitHub. And what every bullet here, therefore, represents is literally every feature we ourselves did not have to implement, or wheels we didn't need to reinvent. So how do we go about actually using the platform, and how do we actually think about which of its features to use. So there's a few options when it comes to code reviews alone. So you might be familiar with gists, where you can throw up one or more files and pretty easily annotate on it. The catch with gists, though, is that even if, especially if the file is long, or if you have multiple files, the commenting system is essentially relegated to the bottom of the user interface. And so certainly for newbies, it's not ideal to be talking about a program that's this long with all of the comments relegated here. So they're just sort of, in terms of UX, constantly going back and forth and not actually seeing proximal to what they did well or not well, the teaching fellow's own comments. There's also pull requests. And pull requests are also used if you're familiar with a tool called GitHub Classroom, which we actually seriously considered. We thought, what better way to avoid reinventing the wheels than to build on top of or use this? We would need to add some of those additional features for our various demographics. But ultimately, a model that's used, or we considered, this pull request model was a little too sophisticated for the UX that we wanted our students to have. In the pull request model, the idea would be that students have a repo for the homework they're working on. They would then do their work, push it to their own repo on github.com, and then submit a pull request from their repo or their fork of a main repo to a central one to which I and the teaching fellows actually have access. And then via the typical pull request UI, could we actually comment on their code and provide feedback iteratively. The downside here, though, is that that meant now students had to understand Git, and they had to understand it in week 0, the very first days of the class, which for an introductory course, almost all of whom are or 90% of whom are non-majors these days. It simply wasn't the sort of mental hurdle we wanted early on. And ultimately, too, we didn't necessarily want students having both their own repo and then the staff's repo and trying to explain to them conceptually like why there is, in fact, this dichotomy, because they were the only contributors ultimately to these repositories. And so ultimately, we settled on this approach instead. You might notice that when you push a commit to GitHub or push one or more commits to GitHub, you'll actually see a diff within the UI whereby the pluses and minuses line up with what a command line diff would actually look like. And you can click on any one of those pluses and actually comment on that very precise line of code. And so this UI, under which a teaching fellow could then comment and actually provide his or her feedback, was exactly what we were looking for, but there's a catch. If students are submitting multiple times, and in Git speak, essentially pushing multiple commits, their code might change over time. But a teaching fellow, unlike, say, a colleague in a company doing code review every day or every week or every push, doesn't care necessarily about those deltas day to day as the student is working from start to finish. We really, for the course's purposes, only care about the end result. And unfortunately, if we now have to go through n different commits and UIs like this just to see the various deltas from the first day of the week to the last day of the week when the student finally submitted, that too wasn't ideal. We wanted to actually have access to the full code and provide an entire review of their code ultimately. So what did we ultimately go about doing? We signed up for a GitHub organization, as you might have yourself. We then went to education.github.com, whereby you can actually flag an organization as educationally oriented, which means we did not have to pay for the private repositories, and there's also no limit. And I dare say one of the challenges for us is finding a Git hosting service that can tolerate tens of thousands of repos in the organization. Perhaps not a common problem within a typical org, but indeed that was something that was possible here. And then we had to decide this. Once we had decided that we wanted students to have their own repository in our organization so that we had full control over it, API and otherwise, there became this question. So do we give students one repo per project, or do we use one branch per project? Like, the norm would absolutely be to use one repository per project or per homework assignment. The catch here is that we have 9 of these during the course of a semester. The students are seeing Git and GitHub for the first time. We have, say, 50,000 repos right now in the organization. So even though it's a constant factor difference, the difference between 50,000 and 450,000 repos is kind of significant, especially when these projects only have a life of maybe 1 week long, and we're not contributing to them over time. So considering one branch per repo was an option instead. And in terms of what the UIs would have been for students, is if they went to our organization's page, they could have searched for their username and seen only those repositories to which they have access. but we would have needed to come up with some naming scheme to avoid collisions so that every student could have some unique identifier for the exact same problem sets. But we noticed there is this. As you yourselves might know from GitHub's own UI, there's a very pretty simple drop-down menu via which you can toggle among branches. And this was exactly a feature in our own coding review UI in CS50 Submit some years ago. And so we realized maybe we could start to leverage even this piece as well. And so if you'd like to take a look at the code ultimately that we put together, thus was born Submit50, the command line tool to which I referred to earlier, that essentially wraps and therefore abstracts all of the Git commands that students themselves would have had to write or execute back in our GitHub FI days. And it also handles a lot of various corner cases. For instance, we use a separate git dir. We essentially put their code into their Git directory into /temp so that it does not collide with anything in their local directory. And we do a number of other tricks as well, as I'll show. So this is the user experience for a student. Here is our so-called CS50 IDE from Cloud9. This is a terminal window simply maximized in the screen. And the student is currently in a directory called workspace/hello, where he or she might have a file like hello.c or any other files. They'll run submit50 hello, where hello in this case simply represents a unique slug or technically branch name to which the code will be submitted. They type in their GitHub username, their GitHub password, and then they're prompted, as here, to confirm which files they're actually going to submit using another wonderful free feature of git ignore files. By storing these git ignore or exclude files server-side, can we also finally start blacklisting all of the binary files or core dumps that we actually don't want, whitelisting and requiring files that we do actually want. Students are prompted whether or not they indeed want to submit these files, and if they confirm as much, they have submitted, in this case, hello. And all that has done effectively is the requisite git commands underneath the hood. A git add all, and these are somewhat simplified to keep things simple. A git commit with a message that we define for them, and then a git push to specifically the branch that they specified at the command line. And if they resubmitted, and simple though this is, and baked into Git though this is, this was one of the very serious challenges some years ago when students were moving dot files or not noticing when they move files around that there was a .git directory or others, simply doing a trick like this whereby we do a bare clone of the repository. So even if they're on a brand new machine and their code has somehow made it to this other machine, do we clone whatever submission history they actually already have? We update our reference to head and actually then push the latest version of their code onto it. Because here, too, we ultimately do not want, in this case, to just see diffs of students' code. Ultimately, we'll see that we want to be able to provide those same comments. And so by leveraging, ultimately, the GitHub API, specifically the repos set of functions, we're able to achieve a user experience for students like this. So this is our Submit50 organization, a user like J. Harvard for John Harvard. And this is an example where the user has submitted his hello assignment. You can see a little drop down here where he or she can select what branch it is they're looking at and therefore what homework assignment they've submitted. If you select from that, you'll see that it's not just hello, but 3 other assignments that J. Harvard has submitted in this case. And then, using that same API, we were able to leverage releases in a somewhat unusual way, but compelling. If you look at the Releases tab, via API calls, when students pushed their code to github.com using the Submit50 script, did we edit a little markdown dynamically using GitHub's API, updating a release for their hello program so that each of these links here, code, comments, and commits, is ultimately allowing the student to click on code and get to his or her appropriate branch, clicking on comments to get to the diff that we're about to see, or get to the actual commit history that he or she has if they want to review the actual diffs over the course of the week that they made. And this ultimately is the goal. As simple of an idea as this is, the ultimate goal was to provide students with this kind of experience and in turn their teaching fellows with this experience so that they could comment on each and every one of those lines, like in this case here, doing it inline, unlike at the bottom of a gist or via some other UI. So how do we actually provide access? Well, if you've used GitHub permissions before, you might know that you can give a particular user as a contributor write permissions, as J. Harvard might need. A teaching fellow, username TF here, read permissions, so he or she can actually review the code, and certainly any number of other teachers that might need it. Via webhooks, did we install in the Submit50 organization a hook that results in every github.com payload being sent to one of our servers so that we can execute certain commands. And this, for instance, is the magical incantation that we use to create full file diffs. Again, if a student is doing multiple commits over the course of the week by submitting his or her work again and again and again, you would get one commit for the changes they made up here, another commit for the changes they made down here, another commit for the changes down here, and so forth. We want to see entirely in green the student's code. And so can we do this by essentially using what are called orphan branches, or this approach here, so that we essentially decouple the last submission from their first submission, squashing everything together to create the illusion that it was just one big commit. And we use tags so that the teaching fellows, per the UTC timestamp here, can go to a very specific time at which the student submitted their code. But perhaps the most exciting part ultimately, certainly in terms of saving human time and providing students with a process much akin to like a CI/CD process whereby there's an automated suite of tests that gets run against their code, do we also have this tool chain as well called Check50, another command line tool that students can run at a command line in order to auto-grade their work against a testing suite that we write on the back end. And doing this is implemented on the server essentially as these kinds of commands. As soon as a student runs submit50, and his or her code gets pushed to github.com, thereby triggering a post-receive hook that tells CS50 servers that there is a new submission. We essentially run these commands in the context of a few others where we clone that repo, specifically checking out the branch, or rather the tag that the student had just submitted via our hook, and then run this command check50, which is independent of GIF itself, but is triggered simply as a result of that hook. But a challenge we had years ago was when you've got students' code on your servers, and now you actually want to test it, and you want to test it without human eyes auditing the code even a priori, where and how do you run this, especially when you have tens of thousands of humans taking a class who you don't know, and for whom it would be a delightful challenge, we presume, to try to take down our services or be more adversaries than they are students. So we needed to sandbox students' environments in some way. And so years ago, in the first version of this, back in 2012, did we kind of cobble something together ourselves. We used a few Amazon Cloud virtual machines, and we used like a CentOS, and we used SE Linux, which is an utter pain to actually configure, and actually tried to create a fairly isolated environment with IP tables for firewalling and a whole bunch of mechanisms to avoid students rooting the machines and generally impacting other students. Fast forward to present day, we've been able to throw a lot of that away by using Docker instead, with containerization technology, whereby if you're familiar with virtual machines, the topology for which generally looks like this. You've got an infrastructure like your hardware or bare metal. You're running a hypervisor on that, which would be like VMware ESXi or something along those lines. And then you can run 3 virtual machines, each running its own operating system with its own software installed and its own application running. Docker you can think of as a lighter weight version of this, whereby you run Docker, on top of which you run only different software layers that give you slightly different versions of a base image that you might have. So they all share some common kernel or some core of the operating system, but it's much lighter weight in that you literally, as per these pictures from Docker, don't actually need 3 versions of Linux or Windows or some other OS actually installed on the host. So via Docker, have we been able to actually automate the sandboxing and the testing of students' code so that after they've submitted, after it's been cloned, when Check50 runs, it's running in an environment quite like that depicted at right there. And where do we do this? So there's a number of cloud providers these days. Docker itself is becoming fairly commodity on various cloud platforms. We happen to use Amazon ECS, which is their Elastic Container Service, which just means that it's pretty easy these days for us to start and stop containers as we need, which means the moment a student's code has been cloned, we start a container, mounting their directory inside of that container, and run it essentially in isolation of everything else. So the high-level description of where we're now at is that a student pushes his or her code to GitHub via submit50, that command line. A post-receive hook informs CS50 of that submission via our back-end server that's always running. We, in turn, that server, inform Amazon's container service that there has been submission so that ECS itself can clone that repository, auto-grading things inside using Check50, and then ECS via another callback webhook essentially tells us, CS50 and our main server, of the scores so that ultimately we're able to put into our own database any of those final results. And so I sort of admitted before that despite this wonderful trajectory of homegrown, 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 not homegrown, we kind of added some homegrown at the very end. The moral of our story ultimately has been we have only implemented that homegrown solution for those pieces that are very specific to us and that are not commodity and that are not shared among all CS courses most anywhere, certainly operating with lots of students online. And so we've actually done away with using the GitHub releases approach because this wasn't the best UI for the teaching fellows who'd much rather see a menu of the work that they need to be done. And so this is a screenshot, thanks to our team, Brian, especially back home, whereby this is what our teaching fellows now see, where every timestamp in that dropdown represents a Git branch or Git tag, each of which has been timestamped per that workflow earlier. You can see at the far right the little checkboxes that indicate this code has been automatically checked. And so our teaching fellows can now navigate via this UI and then ultimately even input their grade. So this is the one thing for which there's probably not a reasonable feature request of GitHub to support sort of writing arbitrary data to repos like grades in this way, akin to a database. And so we store, for instance, a correctness score, C, a design score, D, a style score, S, and that simply happens to be in our own SQL database. But you can see there the branch names that map directly to what it is that is being stored on GitHub. So long story short, if you'd like to take a look at or contribute to or fork or use any of this, see any of these URLs here. I'm happy to stick around for questions. But again, if there's any takeaway and message we'd like to convey is to not do what we did for years, which is implement homegrown tool after homegrown tool, and whether it's GitHub or something else, try to stitch together and piece together via hooks and all of these modern tool chains solutions to problems that you yourself might have. So thank you so much for coming.